So last class we were discussing about different types of projections. The geometric projections are classified into two categories, parallel and perspective. And again, the parallel is divided into orthographic, axonometric, and oblique projections. So in the case of orthographic projections, you can able to get different views of an 3D object. Either it can be a top or bottom view, front or rear view, or right side or left side view. You can able to get it. In the case of axonometric projection, it's further classified into three different categories: dimetric, trimetric, and isometric. And when it comes to oblique projection, cabinet and Calmia projections are the two categories we have. And another major category of projection is an perspective projection. It's categorized as 1 point, 2 point, and 3 point. I think we have started with orthographic projection. I have given you the basic preliminaries with respect to projections. You should know what is the center of projection, projection plane, and projector. The center of projection is the point from where projection is taken place. It can be either from light source or an eye. Plane of a projection plane or view plane. The plane on which the projections of the object is formed is called the projection plane, and the projector's line emerging from the center of projection and hitting the projection plane after passing through the point in the object to be projected. So this is the projector. So these three points is very important with respect to the projection. Coming to the categories, in the case of parallel projection, the center of projection is at infinity position. All the projectors are parallel to each other. So you can see these are all the projectors. They are parallel. They are not converging at any point. They are in the infinity positions. In the case of perspective projections, the center of projection is at finite distance. So you can see the center of projections are in finite distance, and also the projectors are not parallel. It is not parallel. So example is specified here with the help with the center of projection. As I told you earlier, two different ways we can project the object. Either you can make the center of projection fixed and the object can be rotated so that you can able to view the different views, or object can be kept as fixed and the view plane can be, or the center of projections can be movable, by which you can able to get the different views of the corresponding object. Coming to the orthographic and oblique projections, the projections is perpendicular to the view plane, whereas the projector are inclined with respect to the view plane. In the case of oblique projections, it is perpendicular, it is inclined with the view plane. So we will discuss some examples, some problems related to this, and then we will move on to the slides again. Orthographic projections, the view, either you can see the top view or the front view. Based on the view direction, it is changing, and side view you can able to see. So as we discussed three different projectors with respect to parallel, we will move to the parallel projector one by one, how we are forming a different objects based on the orthographic projection, and then we will move on to the other things. In the case of orthographic projector, the projector are perpendicular to the projection plane or a view plane, and hence true size and shape of a plane face of an object is obtained. So you can see the object, whatever we are having, it's going to be same size. Whatever you are viewing from, it is projected as same size. The size and the shape of the object will be same. So mainly this kind of parallel projector or orthographic projectors are useful in the case of engineering drawing. So the projection can be either in any one of the coordinate plane, either it can be x equal to 0 or y equal to 0 or z equal to 0. So with this we can able to write a transformation matrix. So the transformation or matrix for the projection, it's a projection matrix we are able to write. As we have discussed earlier, in the case of transformation, each and every transformation we are writing a kind of matrix for performing the operations. So similarly here also we are making a projection matrix. So P is the projection matrix, the projection matrix onto the x equal to 0 plane. So x value is 0, y and z value is as such. So this is 3 cross 3 representation. X, y and z values are represented here. We can write this in the form of an homogeneous coordinate. So when you make this 3 cross 3 into homogeneous format, it becomes 4 cross 4. You have 0, 0, 0, 0, 1, 0, 0, 0, 1. And the last terms will be 0, 0, 0. So we expanded 3 cross 3 into 4 cross 4 for making the multiplication operation. This is done. So here it is with respect to x equal to 0. When y equal to 0, you can again write the equations or the matrix you can specify where x value will be there and y value is 0 and z value is 1. When it comes to the projection on z equal to 0, z axis value is 0. So these are all the three matrix we have for the projection matrix we have. So when we to visually reconstruct the shape of an object, single orthographic projection does not provide the sufficient information. So for this, what we are going to do is we are having multiple orthographic projections based on the needs. So when you wanted to display or when you wanted to see front view, right view, right side view and top view. So what kind of projections can be applied out of this three? Front, right and top views are obtained by the projection onto which planes? Any guess? You want a representation with the object? You want the representation with respect to an object?
Ma'am, should right be y plane?
Yes, ma'am.
Yes, I'll show you the representation. 1 minute. So you can able to see the object?
Oh yes, ma'am.
Yes.
Yes, ma'am.
So this is one plane and this is other plane and you have other plane here. Okay. Now I wanted to see this object. So which plane value is equal to 0 such that x and y, one plane value is 0, the other two plane value will be there. So which value is 0 so that I can view the top view?
Y.
Why? I wanted to see this. This is corresponds to which? So let me take a cube, then it is very easy. Rather this object, let me take some object like cube. Yes, maybe this object may be clear. One axis, other axis, other axis. So you have to, with some objects, you have to check it out. Then only you can able to understand the concepts, because it's very difficult for me to explain here. So you have here one axis, other axis, the other axis is this direction. I wanted to view this, which is maybe you have, I will draw another representation with so we have a representation x-axis, y-axis, z-axis. So now you can see I wanted to view this direction value. Which value is 0 now? This is now your top. My screen is visible. Not
Yes,
top.
ma'am, it's visible.
Yeah, this is top value, and I have asked you the question front, top, and right side. I'm right? Yes, for
Yes.
viewing the front side, front portion.
Like what
Z.
will be 0?
Z is 0.
Z axis.
That is 0 for front view. What about right?
X is 0.
X
X
is
is 0.
0.
X equal to 0. And top?
Y equal to 0.
Y is equal to
0. Okay. Now, what is the viewing point or the center of projections, center of projection for this? From which direction you are viewing? So you have said 3 answers. The front, right and top view are obtained by the projection onto z equal to 0 and x equal to 0, y equal to 0 plane from the center of projection at infinity on the respective axis, z axis, x axis and y axis. So you have two axes, positive and negative values are there. So positive x axis and negative x axis is there. Positive x, positive y, positive z and positive, both negative and positive values are there. So you are viewing from the center of projection at the infinite on positive z, positive x and positive y axis respectively. Suppose you wanted to view the other cases. They are, I wanted to see right side we have already completed. Suppose we want top is there, rear, left side and bottom view. So for this view, what will be the projections where you have to project? The projections are obtained by projecting
On the negative axis.
z equal to 0 and x equal to 0. Similarly, y equal to 0. But what
But
about
viewing
the
from minus
yeah
x.
from the center
Negative
of
axis.
projections, negative axis. So this uses negative of the corresponding axis. This is positive of the corresponding axis. So it's clear.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So when we see the projections, either projection on z-axis, positive z-axis or negative z-axis, whatever the axis, you can able to view only one side of the one face of the object. It has 6 faces, but you can able to see only one face at a time when you are using any one of these projections. Yes or no?
Yes, ma'am.
Yeah. Front and front and side views are, you can call this as an front elevation and side elevations, or top elevations, you can call it as an plane view. So suppose you wanted to see all 6 views. All 6 views can be obtained by, how can you obtain all the 6 views? Is it possible? When you use
Not at
one
the same
projection,
time.
all 6 views can be obtained with the combinations of whatever we have studied in the previous case. I mean, previous case in the sense transformations. That's why we have studied a transformation. So all the 6 views can be obtained by combination of reflection, translation, and rotation, followed by projection onto z equal to 0 axis from the center of projection at infinity on plus z axis. So we can able to do this set of transformations to view all the 6 views of a corresponding object. So we will solve some problems related to this problem, in the sense it's not an issue, just a geometrical problems, we will mathematical problems we will see. Problem 1. To find orthographic projection of an unit cube onto x equal to 0 axis plane. To find the orthographic projection on a unit cube onto x equal to 0 plane. So where we are projecting here, what is the information specified to us? They have given an object. Object is specified as an unit cube, and another information we have is an projection plane, x equal to 0 plane. We are going to project it. So from this you can able to write down the coordinate values. So I can make use of this cube itself. So what I will number this so that it will be easy. The vertex are numbered with ABC, named with A, B, C, D, E, F, and GH. So what is the value you have here? It specifies as unit cube. So every directions you will have length of 1 unit. What is the value you have here? This is the origin 0, so you will have 0, 0. And what about the other values here? What is the value you will have here in the F? F has only x value, y and 0 values are
1, 0,
0, 0. Yes. So by this way you can find out the values of each and every vertex of the cube. This is 0, 0, 1, and this is 1, 0, 1, and this is 110, 010, and this position is 1011, and C, it's a combination of all the three. Whether all the values are numbered? Yeah. So we have obtained the objects in with respect to origin. It's an unit cube. So in all the direction it's 1, otherwise it's a 0 value. So we have constructed. So from this we are now making a matrix representation. So directly you can do it. Just we will make a matrix representation so that the process will be easy for performing a matrix multiplication here. We have X. X is a set of inputs. We have we can write down the coordinates values of A, B, C, D, E, F, G, H. So just you can copy it from there. And the question says now we have found out the coordinate positions of each and every vertex of a given object. Now we need to perform the transformation. The transformation is performed, projection is performed with respect to x equal to 0 axis. We know what is the matrix we have for transformation. The matrix for transformation is x values are 0 and you have other values for other x, y and z values will be 1, and this is the value we have obtained from the given data. And what we have to do right now, we need to find the orthographic projection. So to compute the orthographic projection, that is new projected coordinate x dash is then orthographic value, which is x into P projected value. So we are making this to be multiplied. So you can make everything as a homogeneous coordinates. So you can use 1, 1, 1 for all these things. And this can be 0, 0, 0, 1, 0. 3 cross 3 is converted into 4 cross 4. And the homogeneous coordinate values. So you can multiply these two things. What is the resultant matrix you will have for x dash? Which is A dash, B dash, C dash. So multiply and tell me the resultant matrix. What is A dash value? I'll write down A, B, C value so that it is easy for you to multiply. Okay, it's clear, no? Whatever I'm writing, it's going in some direction. You can able to understand, no? Yes.
Yes.
So the resultant matrix after multiplying x with the projection on x-axis, projection on x equal to 0 plane. So we can able to get. So from this, without multiplying, you can say what is the value you are going to have in x dash, x value, x component, coordinate value of x, y, z, and homogeneous coordinate. The homogeneous coordinate is going to be 1. What about the x value you are going to have?
X would be 0 always.
All coordinate x value will be 0. So y and z, either it can be 0 or 1. So you compute it and you can verify it. Now you can see this is the original object. Here it uses x, y, z value. But this 3D is now converted into an 2D. For viewing purpose, we are converting this 3D into one 2D. So it has only y and z coordinate. X coordinate, all the values are 0. Similarly, you can do it for y equal to 0 plane, and similarly for z equal to 0 plane you can do, and you can see. So when you do this, you can able to see either whatever we have in the earlier case, either the front or right side or the top view of an object can be viewed. So the orthographic projection is mainly for getting the different views of a 3D object. Next is in second category. Yes, orthographic is over. Now we are moving on to axonometric projection. So the main limitation of orthographic projection is unable to illustrate the general three-dimension shape of an object. So we are going to construct a object by using an axonometric projection by using rotation and translation. So we are using a rotation and translation we are using here to manipulate the object such that at least 3 adjacent faces are shown, and then the result will be projected onto the z equal to 0 plane, or any one of the plane you can project it. So here we have another thing, one more, then you can project it. So the axonometric projection shows its real shape only when the face is parallel to the plane of projection. The plane of projections are equally foreshortened. With this foreshortened factor, we are going to discuss the further category of axonometric projection. The foreshortened factor is the ratio of the projected. It's a ratio of projected length of a line to its true length. So projected line by true length of an object will give you a factor which is called as a foreshortening factor. We have types: trimetric, dimetric, and isometric. So when it comes to a trimetric projection, it is formed by arbitrary rotations in arbitrary order about any or all of the coordinate axis, followed by projection onto z equal to 0 plane. So it is formed by arbitrary rotation in arbitrary order about any or all of the coordinate axis and followed by projection on z equal to 0 axis. So let me discuss this. So we have representation, as we are talking about the previous case. We have a matrix representation here. The trimatric projection, the foreshortening factors are obtained by applying transformation matrix to the unit vector along the principal axis. So you need to have a unit vector. This is an unit vectors. All the principal axis values are 1. That is unit vector along the principal axis. And as we said earlier, it is represented as homogeneous coordinate. So we are introducing an homogeneous coordinate factor here with t. So I can make a note u into t, where u is an unit vector along an untransformed xyz axis, where t is the trimatric projection matrix. So what this t is going to have, let me write t equal to xx y x the projections are performed on z axis. So z value is 0 and x and y value you have some values. So we can multiply u and t to get the final result. The final resultant matrix u into t we can multiply and we can get the values. This value we can get it. So from this we can able to get the foreshortening factor along the projected principal axis. So these are the factors we are obtaining. So after multiplication you will be getting the multiplied values as this. With respect to this is x. Similarly, x y dash plus so this way we can able to write the values for foreshortening factors of each and every principal axis. So from this information what we can infer is we have three values, three foreshortening factors. So you can see all these three values are it's a based on this whether it is equal or it is different. Based on that only we are going to say whether it's a trimatric or dimatric. So when it comes to one dimatrix, it's in the case of dimatric projection, two foreshortening factors are equal and third is an arbitrary. When it comes to an isometric, all the dimatric, all the foreshortening factors are different. So the dimatric is constructed by rotating about y-axis through an angle phi followed by a rotation on x-axis with some angle theta, and then we need to perform a projection on z equal to 0 plane. In the case of isometric, So all the three factors are kept equal in the case of an isometric. So we can able to get the informations, the we can able to get the angle that are projected x-axis makes an horizontal is important in manual construction of isometric projection. Transferring the unit vector along x-axis using an isometric projections yields and matrix. The matrix is on x-axis, as I told you, transferring the unit matrix along x-axis, so only x-axis value, using the isometric projection yields it's u into t, as we have discussed earlier, the same cases, but here the t value will be different because rotations are followed with some operations we are using. So the matrix here is this. So I'm just writing out this. I will be giving an example also. So I'm not dealing with the derivation part of it. Just I'm writing out the matrix as such. So three different types of axonometric projection. Generally, when we talks about an axonometric projections, it is performed by rotation, translation, and then you can project the object on z equal to 0 plane. We can make use of an foreshortening factors. The factors can be of same value in all the direction, or two value may be same, or three values are different. Based on that, we will be able to get trimetrics, dimetrics, or isometric projections. We can able to get u dash, which is equal to u into t, where t is the unit matrix and t is the projection we are going to use. If it is trimatrix, we have some only x and y values we had. When it comes to one isometric, we have some cos and sine value, rotation values are there. If it's a dimatrix, I forgot to write with respect to dimatrix. The t value for this is for dimatrix. It uses a rotation, two rotations followed by the projections on the z-axis. So after rotating it, we are getting this. So by this we can able to write the foreshortening factor, that is fx, fy and fz, which is a root of cos square phi plus sine square phi into sine square theta, and y is cos square theta, and fz is sine square phi plus cos square phi sine square theta you will get. So this is the foreshortening factors we get. In this you can see xy equal to cos square theta, square root of cos square theta, and the remaining two factors are same. So when you multiply this, and if you able to see all the three factors, you will get as a one values, which is cos phi, sin phi, sin theta, 0, 1. Finally, after multiplication, you can able to get this value. So this foreshortening factor, we can say whether it's all uses the same factor or different factor, or two uses same or one uses different. Based on that, we can able to say. So I will be showing the PPT. And next projector is oblique projection. As we know that the the projection is perpendicular to the view plane, you can call it as an orthographic projection. If it is not perpendicular, it is inclined with some other angle, then you can call that corresponding projection as an oblique parallel projection. And an example is specified here. So with this, we have two different kind of oblique projection. One is Calvia projection. The degree of projection is at 45 degree, and cabinet projection with the degree of projection at 63.4 degree. So this shows you the clear examples of Calvia projection and cabinet projection. The angle alpha inclined with this is 45 degree. The angle of alpha which is inclined with cabinet projection is 63.4. Next comes the perspective projection. In the case of perspective projection, the center of projection is at finite point. That is the one difference from a parallel projection, and the projectors are not parallel. So that is the other difference we have with respect to the parallel projection. We have different vanishing point. So based on the viewpoint, we will get a different vanishing point or converging points. Either it can be 1, 2 or 3. We can see 3 different points here. It's called 3-point perspective. And the next case is an example for 2-point perspective and 1-point perspective. So in the case of perspective projection, let us represent the transformation as so instead of writing values, let it be some A, B, C, D. H, don't confuse with homogeneous coordinates, so I am removing H here. Something into S. So actually this is 3x3, it is expanded into 4x4. In the case of perspective projection, you can see the value based on this 3 values. We are going to say whether it's a 1-point or 2-point or 3-point. If it has only one value, if a P or Q or R is present, then you can say it's a 1-point projection on corresponding axis. So it should, if you have 2 values, either PQ or QR or PR, then you can say the projections are the perspective projections with respect to the corresponding 2 values, 2 axes. And in the third case, if you have all PQR, all the values, it's a 3-point perspective projection. So we will discuss next class some problem related to each and every cases, how it is going to have the values in there we will discuss, and then we will move on to the rendering part. So thank you. What about your